Hello, 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 hello. Welcome to another episode of Ksa Talk Show. Fantastic. Today we're gonna do Emac Lisp coding and some random chat about type theory. Okay, and this is my keyboard, Kinesis 360, and this one is Ultimate Hacking Keyboard too. Both of them are fantastic. They are super light switches, 35 grams activation force. If you are, if you don't have a mechanical keyboard, go run buy it now. Okay, get a Chinese cheapo buy the linear switch. Okay, so let me begin to talk on today's topic. You go to Kasadi Keyboard blog and you can find all you want to know, all you need to know about mechanical keyboards and ergonomic keyboards. I recommend this Glove 80. I recommend Kinesis 360. I no longer recommend Kinesis Advantage 2. Okay, so Glove 80 and Kinesis 360. And I recommend Expose Night and this Apple Maker Faker Alice 80 is actually pretty good, although I don't have it, so I don't actually have experience. And Ultimate Hacking Keyboard, okay? I recommend these keyboards. And this Kinesis Freestyle is actually pretty good too. So run and get one. If you don't have, some of these cost $200, $100, $200, $300. So if you don't have that much, you are a student, if you are a programmer, you should buy it, programmer, because this keyboard is your life. Okay, you don't want to see a doctor for your hands problems. But if you are a student or you don't type that much, so first of all, go get a normal mechanical keyboard. So just go to Amazon, buy a cheapo, Chinese cheapo. But the ones here are very, buy this one, for example. This one is like $60 or something. Optical switch, very good too. But the looks is the gamer look, the zoomer gamer idiocy. They have to name their keyboard Bloody. Like, oh, Bloody, this must be good because teen gamers, they want to shoot the fucking idiots. But the gamers, they basically created the whole industry about mechanical keyboard in the past about 10 years. It made mechanical key switches popular. So anyway, so that's enough about keyboard. Let's go back to, let's put a link here and go to Ksa Talk Show today, okay? So today we're gonna talk about type theory and Emac Lisp coding. Okay, if you have comments and questions and any thoughts, say it now. Okay, you direct what my talk show. Okay, I see your questions, I answer or start to talk in that direction. Okay, so Joman, hello Joman, I know you, Joman. Zubribu, hello. Zuribu XD. I saw you in the last couple of my videos. Okay, so type theory. Okay, I've been reading a lot. So should I, so two topics today. We're gonna do Emac Lisp coding. And so what is the topic for Emac Lisp coding? The Emac Lisp coding topic is, close that. Okay, so we have several image. We're gonna code something about processing images within Emacs. Okay, so which topic do you guys want me to go? Let me just go, because every time I ask, there's a delay, and I don't get the answer. So Emac Lisp coding and type theory. Let me just talk random. Okay, type theory. So I've been spending like 30 hours in the past few days reading type theory. This time seriously. So this is, let's put it into this is my New Year's resolution. So I really want to understand type theory, which is part of logic. The type theory, proof theory, category theory, they are all kind of part of logic. mathematical logic, and they has to do with the foundation of mathematics. This is very interesting, foundation of mathematics, logic, type theory. You might ask, why do you need it? For example, most of my followers, you guys are programmers, right? So programmers, you code C, C++, Java, you have compilers, the machine don't lie. Machine just manipulate bits, logically. They not like humans. You get tired, you got sloppy. They are always precise. So if we have all this Java, Java, C++, why can't they just automatically prove everything in the world? Because they just follow logic, right? That's an issue. Why can't they? Like sometimes I say, C, C++, Python, they actually don't have a spec. Okay, so what does that mean? Some people will say, they do. Look, Java virtual machine specification. But so as even Haskell don't have a spec. So I mean, the question is, they are so precise. Then why can't you just solve? You can just, use all the Google machines, solve all the world's problems, prove everything in mathematics because you have like so powerful machine. That's a problem. You cannot do it. We can't do it, because this. Why can we not do it? Because that's when all this logic and type theory and category theory and proof theory and model theory comes into play. So you wanted to know, why can't you do it? God, I lost my train of thought. I'm going into a direction that so you cannot do it. Let me give you a example. Okay, so let me. Okay, this is not a good way to go because I'm gonna get myself into a hole. So why can't you just prove everything in the world with C++, for example? For example, can you prove some simple thing? We know already because, for example, some simple thing. Can you prove that I'm writing a program? Okay, so let's see. I'm writing a program. So, for example, given a file path, let's say this Twitter. Okay, copy the file path. I'm using Emacs, but you can do this in C, C++, Java, Python, right? So I'm writing a program. I press a key, then it becomes a link. Okay. So let me show you. So show in talk show. So you can see right now I got this Twitter link. I want to make it a clickable link. So I write the Emacs function. I already did. Press a key, it becomes that, and show in browser. Okay, so it becomes link. So question: how can you prove that your command, this function, is correct? Right? So we have a question that, computers are based on CPU, complicated GPU. They are bits, they're never wrong. 1 in a billion, 1,000 billion times, maybe there's some error, bug, but usually they are never wrong, right? The machine don't lie. So, but yeah, so we have the question about why can't it just prove all the human problems? Like who is correct? Who is wrong? In the world, among politicians, you just run a program, and the program will say, "No, you are wrong," or "He's wrong." Why can't we do that? Well, the simple example. So I have this command that does turn a link to turn a URL like that into a HTML link like that. How can we prove that this command is always correct? You see? That's a very simple question, practical. You can understand what it means. How can we prove it? The computer is so powerful, So how can we prove this command always works? Let's try something. This is not URL, but if we do it, okay, we got error. Okay, we started to get into, the details. So, okay, so this URL must be we know that it must be a particular form. Okay, so what if it's that? Okay, is that a valid URL? That's a question you can look up. But anyway, let's try our command. What it does? Oh, it works. It works. Let's make a link showing browser. So you click there. Of course, it's not a valid URL. So having trouble finding a site. So you started to get into issues. So for example, we know, first of all, this URL cannot just be any string. It gotta be like in a URL form. So, but what exactly is a URL, valid URL form? Well, that's getting more complicated. So that's the first thing. Then, now if we assume this URL is always correct, okay, a valid URL form, then can you prove the command I just wrote always works? For example, let's say, some URL have things like that. For example, Google search. Something, let's search Google, okay? So you search some in Google. So copy the URL, paste the URL there. So this will work. Let's try it. Oh, it seems to work. But some for example, let's show you, okay? Let's go to my Unicode blog. Okay, so Unicode, the mark of human animals. Comments, okay? So, you go to Unicode search, then let's say search for MONS monster, okay? So you got that monster emoji. Copy the URL back to Talk Show, paste the link here, that's a link. So let's call our command. Oh, error something 85, file not exist. but this is a valid URL, so what's going on? So you see, you started to get into complications. You start to, what is a valid URL, what is, and then what is a valid form that your program is supposed to output? Is there a specification? So this is why, this is one of the simple, the most basic reason you can see why, even the computer is powerful, they cannot prove things, okay? The most practical issue for programmers. How can you prove your function is correct? So you get into specification, and what form is a specification? For example, we run into the question about what is a valid URL? That simple question is very complicated because, for example, let me show you the Unix idiocy URL with the Unix idiocy with their request for comment, really fucking common. Okay, so there's URL. So this is Wikipedia trying to explain what that is. Then you go to the living standard. There is a, what the fuck group created by Google and Opera, Scums, and Apple because they want money. The what the fuck group. So you go to living standard and you go to RFC. Okay, wait, let's go there. RFC there. RFC 1738. RFC 3986. Oh my God, RFC 4248. What the fuck? I just want a simple URL specification. What the fuck? RFC 4266. You see? So let's look at this RFC. So now, the URL living standard. Oh my God, how many pages? This 1 million pages. The URL specification. So for this simple thing, you got these problems. Okay, then request for comment idiocy. That's a Unix idiocy, RFC. Okay, the Unix people love to cite this for like 30 years. Not so much today because the Unix hacker generation died out. Replaced by Malan Zoomers, which is don't know nothing and don't care about nothing. even worse. So anyway, you see the RFC 1738 network working group request for comments. Fuck their ass. Uniform resource locator. Okay, status of this memo. Abstract introduction. This 1 million pages of it. Okay. For the most simple issue and references, Jesus. A URL is just a format of certain strings with certain where can you place certain characters, but they have like 1,000 pages, and this is not it. Then so RFC 1738, then RFC Uniform Resource Identifier, URI. Oh, this is different from URL. This is URI. Request for comment 3986. Okay, and this is a million pages of it. Okay, next. Request for comment 4248. The Telnet URI scheme. Oh, so you have URI, but you have specialized URI. Then the Gopher URI scheme, the Mail2 URI scheme, Movie Mail Server URI scheme to historic. Oh, they change. There's also change happening. Okay, so this explains the complication. So the machines are powerful, but you cannot prove a shit. Actually, that's the right way to put it. C++, Java, so powerful, but you can't prove shit. Okay, you can't even prove 1 + 1 = 2. Let me explain about that case. 1 + 1 = 2. You are a college student, or you are a professional programmer, hotshot working at Google. You hear. What do you mean you cannot prove 1 + 1 and 2? For example, you are a Python coder, very popular Python. Let's see. Print 1 + 1. Run it. Oh, it says 2. So you are wrong. Look, Python says 1 + 1 = 2. But this does not constitute a valid proof, because proof goes by logic, so 1 + 1 = 2. So simple question, what is 1? What do you mean by 1? What do you mean by 1? What is the number? Is there infinite number of numbers? All these are relevant questions. Because if you say this proves 1 + 1 = 2, then we can just invent anything. We can invent, from now on, we invent T plus T equals to okay, let's just invent that. Then you can code this in Python, and T plus T always equals to But the problem with that is not useful. So when you want something useful like real numbers, then you have decimals and fractions. You run into lots of issues. So all this comes to the foundation of mathematics. This is when you get formalization, logic systems, type theories, and category theories, things like that. Okay, this is kind of a simple and practical explanation. Okay, let's go back to. Actually, I digressed so much that I did not talk much about what I wanted. I was reading about type theory. So let's go back to type theory. Okay. Skull and Bones says, found you from your site. Love your tech knowledge. Man, keep up the stream. Thank you. Money. Okay, money makes the world go around. All the nice things, doesn't do me much. If you donate, that does something. Okay, so the foundation of mathematics, this is the most funny and the most accurate meme I've seen about logic. So mathematicians for the past 300, 400 years, since 1600, since let's say 1700s, they started to see us seriously. Actually, the history, the foundation of math goes way back 2,000 years ago from Greeks, the Euclid elements. But anyway, so this picture summarize the funny thing about the foundations of mathematics, because you chase logic. Plato says this, all men are male. All men are male. I'm a man, therefore I'm a male. Okay, that's the classic propositional logic. So you begin with that some like 2,000 years ago. Then you started to find problems. You can do this or that. There are issues, logical issues. Then you improve it. But then in the past 100 years, you started to have different. You started to have symbolic logic. That is, instead of using English words, you just replace them by symbols. So you just like almost it's like string replacement. So so logic. What is this? Oh my God, the Zoomer, fuck this guy known professionally as logic, insulting a rapper, the rapper. So here's Wikipedia on logic. So you replace symbolic logic or mathematical logic known in the past 200 or 100 years, invented. So you replace words by symbols. So you capture just the essence of the mechanism of logic. So if P, then P implies Q, therefore Q. Okay, so you don't have to say all men are male, I'm a male, therefore something. You just P a proposition, and if P implies Q, then Q. Okay, therefore. So you symbolic logic. Okay, so then you got problems. You got it's not it cannot capture certain things we want to know is true, such as 1 + 1 = 2, or cumbersome. Then you replace something. Okay, then you have well, anyway, I'm not gonna go into but basically that's how in the past 100 years you have basically tail chase like this. Okay, endless tail chasing. It's almost like going a circle, but actually it's not going a circle, because then you realize, because actually what happens, you started with this logic, then you realize, but there's a paradox. For example, the most famous is Russell's paradox. Let this be a set that is the set of all sets. Okay, it defines a set. What is a set? A set is a set of things, a finite or infinite. I forgot which. But anyway, a set. So this set, we define a set X. Let's say it's defined by this set is a set of all sets. Okay, but is X itself a member of? Is X itself a set of all sets? Things like that. Russell's paradox. Okay, so you run into that problem. So Russell, he's writing Principia Mathematica about 100 years ago. He got this paradox. So in order to avoid that contradiction paradox, so he created type theory. So what he says is that you cannot define something by referring to itself. Okay, this set is the set of all sets. You can, that's referring to itself. So you cannot do that. So you classify sets into types. So you have hierarchy of types. So this level 1, you have sets. Then level 2, you can talk about level 1 stuff. Okay. Then level 3, you can talk about level 2 or level 1 stuff, but you cannot define something in terms of itself something else in its own level. So you started to have this type hierarchy. Very complex because you logic, you go into it, then he found that this doesn't work, or you have to amend it, or then getting very cumbersome and elaborate, and also you made mistakes, things like that. So it's like going around circles. But actually what actually happens, you discover some problem, you went on to the next level, you try to fix it, then you got something else, then that has some other problems. So you started to fix that and reconsider and come up with a new thing, category theory, type theory. Then okay, type theory. You started to have lambda calculus. Okay, oh yeah, but it's you got this problem, so we have typed lambda calculus. Yeah, but that got issues too. So we have you have what's interesting is the then you have these variations of type systems. So you look up lambda cube, on the lower left is the lambda calculus, then you have typed lambda calculus, then you have anyway. So yeah, I'm not an expert of this, but I've been studying logic like casually for the past 30 years. But anyway, I'm kind of going nowhere. So what's your thoughts about how long have I been? Already 30 minutes. Shit, I wasted. Is it I'm wasting, like I'm going nowhere? Okay, so what do I want to say? So what's your thoughts about logical languages? You mean like Prolog, because essentially that's the only thing, almost. Prolog and Mercury. Okay, that's a logical language, okay. And what's my opinion about it? I don't know much about it. I mean, okay, so let's see logic programming. So what are the other logic programming languages? So anyway, so logic programming, that's all this logic proof theory. So they, of course, they went into programming languages, and then of course today we have Haskell and a bunch of others, ocaml, and they all kind of came out of the math foundation studies, including Turing machines and lambda calculus. But anyway, what I want to say about, let's go back to type theory, okay? Maybe that's it. I'm just random stuff, okay? So type theory. So what I can say is that, okay, let me give you guys some recommendation. Yeah, Mercury. So if you are young students, you don't know anything about what I'm talking about, you can learn type theory, okay? There is also category theory, which is very like popular because of Haskell, but I don't recommend it, okay? Type theory, you should go into type theory. And in type theory, there are quite a few, there are quite a few variations, like I showed that, like that lambda cube. There are quite a few, and there are quite a few programming languages modeled based on the different models of type theory, okay? So you can, so if you want to study type theory, you can start to read Wikipedia. That's what I do. Wikipedia is my preferred material as over textbooks. There are a lot textbooks about. Okay, let me show you a few textbooks. These are free math textbooks I've collected: number theory, calculus, linear algebra, real analysis, complex analysis, differential geometry, topology, logic, and proof theory. So you can read a few. A course in universal algebra. You know, universal algebra is another kind of branch that that kind of deal with foundation of mathematics. So you have set theory, you have type theory, then you have lambda calculus, of course. Then you have the universal algebra approach. Then you have model theory. Fairly complicated. You know, it is fairly complicated to really understand them all. Like, yeah. So anyway, these are some of the books. I have not read them though. But so there's also a foundation of mathematics. Let's open them. Okay, let's show. Then the latest is homotopy type theory. That's what I like. I recommend. Okay, so you can see foundation of math. All these are free books, as in like no copyright. I mean, they allow you to use. Okay, so anyway, I'm going nowhere now. So let's go back to what I want to say. Let's go back to so let's start to do Emacs, okay? So about logic languages, no, I don't recommend it. So if you ask me, I recommend ocaml, I recommend fsharp. Okay, I do not recommend Haskell because it's filled with these pop idiots. Okay, ocaml, fsharp. Then actually I discovered yesterday there's fstar. Very interesting. Let me show you. Let's go to my Twitter. Okay, so I found very interesting things. So this, by the way, so this article, type theory, this one is from the Stanford Encyclopedia of Philosophy, and they have an article on type theory, and it's updated in 2022 by this guy, Theory Conquad. This guy is the guy who created calculus of constructions, which is a branch of type theory. Okay, so they have so many branches. Calculus of constructions. And this branch of type theory, there's a programming language to go with it. Proof system, actual programming language that does mathematical proofs. Very popular. In fact, it's the most popular. The name is COG, okay? So anyway, he wrote this article. And anyway, so there's a new language. This fstar, interesting. So this looks like from Russia. You know, this originated from Microsoft research. F-sharp is a branch of ocaml. Ocaml is a branch of camel. Camel is a branch of ML. ML stands for meta language. That's one of the original language, functional language trying to do mathematical proofs based on type theory, typed lambda calculus. Okay, so you have meta language, then you have standard meta language, or SML, or called New Jersey ML. Okay, so then you have camel, okay, which stand for category something, category something meta language. Then you have ocaml, object category something ML. Then you have fsharp by Microsoft. Okay, then now you have fstar. F# is a functional programming language, but all these ML, SML, camel, they begin like 40 years ago, trying to model type systems. You know, their purpose was to do some proofs, but you know, as we learn more about proof theory, they are mostly just functional programming languages. But so F# is, you know, Microsoft's version of functional programming languages. Then what's interesting is fstar. Now fstar is actually a language designed to do proofs. In fact, it's specialized in program verification. Okay, so this fstar I just discovered, very interesting. And among these proof languages, you know, okay, so let me just talk random. Okay, let's go to Wikipedia. There's a page called Proof Assistants. Okay, so what's a proof assistant? It's basically a programming language that is designed to do proofs. Okay, so there are quite a few now. There is, you know, Coq, we mentioned before, it's the most famous. And there's Hall, higher order logic, which is type theory. You know, there's Idris, there's Isabel, you know. And one of the most interesting I find, I'm going to start to learn one of them this year. So that's my goal. I'm going to try to get, you know, serious with proof systems and homotopy type theory. You know, I've been reading them like so much in the past years. The A in camel is abstract. Okay, so some people know what, you know, I'm talking, you know, they know things I don't know. Okay, object, so category abstract metalan. Category abstract metalan. Object category abstract metalan. You know, so anyway, so among these very, very complex, you see, all these programming languages, they are designed to do proofs. But so many, plus their model, you know, we were talking about type theory and different type of models, you know, different branches of type theory, right? So it's captured by this lambda cube. Then the more general case is the pure type theory. You know, all these names may not make sense when you first read it, but just like every jargon in programming or mathematics, but once you study, after a while, you know. So pure type system is basically the most general. The way they differ, you see, the way all these different type systems, they differ is that, let me explain, you know, I'm not expert, you know, I'm a comedian, okay? I'm a comedian on type theory. So all these the difference between them is that in type theory, you have, you know, like we talked before, you know, Russell's paradox. the set of all sets, right? So he resolved it by creating types, a type hierarchy. So at level 1, you have this bunch of things. And level 2, you can talk about level 1 things, but you cannot talk about itself, okay? So if you want to talk about level 2 things, you need to go to level 3. In level 3, you can talk about level 2 and level 1 things, kind of like that, okay? So you have this hierarchy of types. Now, so it gets complex, how many levels do you need, or is it infinite? Anyway, so back to type theory. So the difference between them is that, okay, so you have level 1 of things, it's called individuals, depending on what year, 50 years ago or 100 years ago or today. But anyway, level 1 things, you have things, right? Usually called terms, okay? Now, in type theory, so level 2, you have types, okay? So you group the terms at level 1 into different types. Type is just like English word, different class of them, okay? So level 2, you have different types. Then level 3, let's say, level 3, you have type of types. So you can talk about what, the different types. So you can talk about type of types, okay? So the difference between this lambda, this so-called lambda cube, which captures different type systems, is about, can the system allow you to talk about type of types, okay? So kind of like level 3 we are talking about, or do they do not allow? For example, the lambda calculus is not typed, so you don't have level 2, 3, and so on. You just have terms, okay? But it turns out, lambda calculus is kind of weak. So you have, so anyway, so you can talk about, you can define a type in terms of terms, or whether it allows you to define a new type based on other types, called dependent, called dependent type theory. You define a type based on what the argument, the type of the term. Okay, so anyway, the essence is that defining a type based on a term, or defining, that's one thing, or another thing is defining a type based on a type, okay, type of type. Then you can also have defining a term based on what type it is. So that's essentially, that's what this gets you, all these different. So you can see the Wikipedia says, this x-axis types that can bind terms corresponding to dependent types, okay? Then another way is terms that can bind types corresponding to polymorphism. That's a computer jargon. That's like when you define a function, what the function return depends on what type is the argument, okay? Polymorphism, Then you have types that can bind types, like we were talking about level 2. You can define a type by another argument of a type. So you have all these different type systems, and they have like different powers and different flaws, and it relates to whether they terminate, things like that. Like there's pros and cons for many of them, because otherwise you can just go to the highest level. Why do you have to bother with all the different ones? You just pick the one that's the best. But it turns out it's not like that. So that is why when you study logic, it's kind of like this, you're going around circles. So so you have all these different models of lambda cube. You have all these different models of type systems. So the most general is so-called pure type system. That allows you define, that allows all of the above, type by type, type by term, term by type. So you can see these symbolic expressions. I love them. Okay, I love these symbolic expressions. Now the C and C++ and Java and Python idiots, try to get the load of them, of these. Okay, Unicode. So this is related to Unicode, so we can go into you can Unicode symbols for these logic systems, for all and exist, therefore, because, therefore, and a proof, not, and, or, and so on, not, and, implies, assert, true, not true. Love them. Okay, then there's binary operations, and there's n-ary operations, and, or, for a bunch of things, not just two things. So there is that. Then you also have, in type theory, one of the symbol, so while I was studying type theory, I was also looking at, the symbols they use, which is very important. You see this vertical line and horizontal line, that's called a tack, T-A-C-K, okay? And that is used, these tacks and turnstiles. Okay, very interesting. Okay, so, and another thing I learned is that in type theory, you have this B, let's go here, okay, you have this, normally we are familiar, if you are into mathematics, you are familiar with this double stroke Z for integer, double stroke N for natural numbers, which depending on the author may include 0 or may not include 0. So that's a ambiguity, the meaning of natural numbers. Some author includes 0, some not. Then P for prime, Q for rational, R for real, C for complex numbers, double stroke font, and you have H for quaternions, which is like 4-dimensional complex numbers. Then you have Sardinians. Sardinians is 8-dimensional complex numbers. Okay, these quaternions and Sardinians are less used. So they are the theories about complex numbers, quaternions, Sardinians. They are part of algebra. Okay, algebra. Okay, then in type theory you have this B. They stand for Boolean. Okay, so this is new. I mean, this is new to me because this is rarely seen in typical math textbooks. They don't talk about Boolean type, but in type theory, you have this B for Boolean. That's interesting. Okay, I rambled a lot about type theory. Let's go to code Emac-Lisp. It's almost already an hour. So now let's go, I want to code Emac-Lisp. I want to, because, this is what I need to do, for my work. So rambles about type theory. Oh yeah, so we talked about, different type theories, very many different type theories, the lambda cube. Then you have proof assistance, okay, proof assistance. So these are programming languages that does proofs. So there are many of them, and they are based on different type theories, different type theories. So you can see Coq, for example, the most famous one, they are based on dependent types. Okay, yes, dependent types, higher order logic. Okay, they are not very specific here, but Coq is, for example, I read it's based on calculus of, what's the term? Sequent calculus. Okay, let's just open it. Sequent calculus, or calculus of constructions. Okay, and calculus of inductive constructions, which is a higher level up. Okay, so you have calculus of constructions, which is one of the model of type theory. Then you have calculus of inductive constructions. I don't know exactly. I don't know the details. Okay, so I'm just starting to learn it. So different proof. So one of the questions is which one you're gonna choose if you wanna study them. So that's the question. That's the question I'm facing. Because I want to start to get into. And some of these, one of the thing I despise is Haskell. In the past 10 years, because the Haskell coders, they don't know nothing. They are programmers. They driveling about monad every day. They don't know not a thing about what is the foundation of mathematics, but they just drivel. So, and so among that community, what you might have heard online is Agda. Okay, is one of the proof assistant, and another one is Idris. These two are probably, you might have heard, Idris and Agda. But actually they are not good. They don't seem to be good. Because when you are looking into a, proof assistant, so-called proof assistant, they are just programming languages for doing proofs. Okay, you have to look into the context for mathematicians, not for programmers. The programmers will tell you, oh, you should use Haskell, oh, you should use Agda, oh, you should use Idris. But you look at, the article, they haven't really proved anything. You want to look at what professional mathematicians accepted in the math world, which have been most used to prove, difficult mathematical theorems. So that would be Coq. Okay, there's some example here. So, so they have an article on which one have done non-trivial proofs. Okay, so Coq is the most old and most famous. Then what I discovered, another one is Ling. Okay, so that's also from Microsoft, Ling. Okay, and I think Ling, where is it? Ling. So this, okay, it's also from Microsoft Research. So I think this is the one I'll try to look first, this and Coq. So they have apparently been used by a few notable mathematicians. For example, the Thomas Hale, I've came to know, he has, he worked at Intel, okay, like designing CPUs, things like that. Thomas Hale, a mathematician, he's very into doing mathematics by computer. So I know, here says he's using it. And also this Kevin Buzzard, I was looking up yesterday, who is that guy? So he did, these are mathematicians, okay? Not from the typical, my audience, you are programmers, you hear about Haskell monad shit. So for example, this Buzzard guy, he has done pure mathematics, specialized in arithmetic geometry, and land program. Okay, that's deep mathematics. So what is he doing? Apparently, he's leading the. He's he's using Lean to for the Xena project. One of the Xena project's goal is to rewrite every theorem and proof in the undergraduate math curriculum of Imperial College London, okay, in Lean. So that seems a good, a good good thing happened for Lean, good recommendation, good advertisement for Lean. And also Lean was used to formalize a new proof by this guy, Peter Schwartz, in the area of condensed mathematics, okay? I didn't even know what that is, but it is a new branch of kind of geometry that tries to create a single foundation for topology, complex geometry, and algebraic geometry. Okay, typically they are in different fields. They have different foundations, different axioms. So this condensed mathematics apparently is, started by this guy, Dustin Clausen, and Peter Schwartz, who tries to bring this field into one unified foundation, something like that, okay? Algebraic geometry, very difficult topics, okay? So if you ask the Haskell people, what are these, they don't know. They don't know a shit, but they babble about, proof, correctness, Haskell. Fuck them. Why? Because it's misleading information. It's fashion. And I truly despise that. Like the C and CPP and C++ and Java, OOP is gonna solve everything. This misleading information, fake news, essentially. So anyway, condensed mathematics by this guy, by the Schwartz guy. So he's also using Lean, and the one of the most popular mathematicians, Terence Tao, is also using Lean to prove polynomial Feynman-Rosa conjecture. Okay, I don't know what that is. Very difficult. That I know. So anyway, it seems Lean is great. I'm gonna try to study them. Okay, I think that's about type theory. What's up? Okay, any comments? Let's start to do Emac-Lisp, okay? So I want to do Emac-Lisp, okay? So let's see, what am I talking about? So yeah, so let me show you what I'm doing, what I want to do, okay? So I have, this is just my random notes on stuff. So okay, let's go to the type theory page. Let's go to the PNG. What is this? Logic chasing. Okay, so what I want to do is, for example, this is Emacs. Okay, let's talk about Emacs now. Okay, say something, guys, if you're watching. Now, Emacs. So I'm using Emacs, of course. I'm using Softlight keys. So here's a source code. Here's a URL. You can read about it, Softlight keys. It's a model editing keys for Emacs, okay? And on the pink window, you can see all my command calls as I call them. For example, move cursor, you can see that's this command, okay? And I'm using a Vora keyboard, okay? So what is the problem? So I have this image. Let's say, so for example, I show in browser, I'm a blogger, right? I write a blog. So I want the icon version of this image. So I can press a key. Okay, it asks me width. Okay, 250. Okay, so it creates a new image and it inserted the path here. So you can see the command I just called is where is it? Oh, it doesn't show. It doesn't show because I called the command by key. Anyway, let's open it. Okay, so you can see your iconized image. Okay, the command I called. Let's do it again. Okay, open it, delete it, remove that. Now, let's see. The command I call to create a icon image is this XHTML resize image. Okay, let's do it again. Call it, paste that, do it. Okay, and it says width 250, 250. Yes. Okay, so it creates icon. Okay, so now I want to modify the command so that instead of just pasting the path here, it will actually paste a link like that. Okay, so now if I go to the browser, refresh, you see I want it to do that. Should I do that? Actually, I'm not sure. Now when it comes, yeah, I want to do that is because it makes my writing blog easier, but I'm not sure actually I want to do that because when you create a icon, you don't necessarily want to use the icon in the same page. For example, I go to for example, I go to my math blog. Okay, so that's the page about type theory. Now go back. Now I go to the type theory section, which is here. Now I can paste the iconized image path. Open it, you see. Now I want to extract the path for this link. Okay, press the key so you can see the command is there. Then go here, paste it. So that's the path, right? Now show in browser, so you got that. Now I press the key, it becomes that. Okay, the command is XAR icon linkify. Okay, now I show in browser, you see now I got this. You have this nice iconized link. So what do I want to do? Do I want to yeah, so now actually I'm not sure I want to change it. Okay, so there is another thing I want to do. Okay, maybe that's it for today. Yeah, let's forget about Emacs. So today is just random talk about type theory. Okay, anything else? Anything else, guys? That's it. Bye, guys. Joman says, what will you like to see added to new version of the Wolfram language? Do you think the compiler will have an important impact? Oh yeah, it's going to be a huge impact. By the way, Joman, are you a Wolfram language coder? So Wolfram language, they just came out with Wolfram language 14, and you read Stephen Wolfram's blog, it's like Jesus, 100 pages. Like each one of his blog takes you 5 hours to read it, to actually have some reasonable, detailed, reading. So each one of his blog is like 50 pages. So this one he's talking about announcing version 14, just came out yesterday. And so I'm using 13, version 13. And, so version 13 is like a year or 2 years ago. So, each version, they apparently in the past 20 or 30 years, they started to add a huge amount of things. It just keep adding it. So anyway, this blog I haven't read entirely yet. You can do so much machine learning, like machine learning, right? I learned a lot about machine learning. So machine learning in Wolfram language, you have one single function to do whatever you want, the prediction or whatnot. So you can do machine learning, visualization, image computation, calculus, and algebra. That's old. Optimization, FEM. Okay, I'm not even sure what is FEM. Geometric computation, and so on. Okay. And one of the big thing in Wolfram language is that and also you can do crypto. Like every algorithm, every format, every algorithm, every equation, any problem that's known to humanity is in Wolfram language. The algorithm may be stream processing, the shortest distance of changing one string to another, the Vinian distance or whatever, everything. As long as it's a known algorithm and useful, it's part of Wolfram language. So Stephen Wolfram says that even him doesn't know like right away which one does what. So it's tremendous. And so reading his blog, I started to read it, but so this article is not just about news of Wolfram 14, but he goes over like kind of give you a overview of the history, the development. Why are they adding things? What kind of things they add? LLM become a big thing last year, 2023, and you have prompt repository. You have prompt engineering. So Wolfram has prompt repository. I haven't looked into the machine learning features of Wolfram language, but it's very interesting. Let me show you a simple one, okay? Let me show you let me show you a simple machine learning thing built in Wolfram language, okay? Because I tried it. So anyway, a lot of things in the past decade, they build in image processing and video processing. You can see. So it's like you don't have to be a programmer. It's for technical people. A lot of people today, they work with videos or images or games. They know technical detail, but they are not necessarily programmers. Like they are not professional programmers. They don't deal with algorithms and all that, but they know specification. So Wolfram language is what Wolfram calls a technical computing platform. So you don't need to solve equations, you don't need to program OOP or functions or whatnot, but you need to do a lot of things, processing images, export, import various formats or transformation, whatever. So that is what Wolfram language has become useful to many of these type of people. So for example, here is a animation. It can generate animation, and it can do the edge detect filter. In image processing, they call that filter. So, and one of the, and this is also interesting, random tree. To generate a random tree, it's a built-in function. Okay, it's not so trivial. It's kind of trivial in Python or whatever language to generate a random tree. But if you want to control the depth, how random is your random tree, that becomes more difficult, because there's a depth issue and there's a number of children issue at each node. So you want to create a random tree that is actually random, with respect to some criteria. So if you want to do that, then that's not so easy. And then Wolfram language actually just also renders the tree, and that's non-trivial. So so let me just do some of that. So what is the question? Would you like to see added? So what do I like to see added in Wolfram language? Nothing. It's big enough for me. Okay, but the aspect about compiling it, that would be nice. Okay, I mean, like, you can compile it, so you create an object just like C and CPP and Java, and that you can pass that to other people, and they can run it without having Wolfram language installed. That has been this idea has been thought about since 30 years ago, 1995, when I was at Wolfram. But there's, anyway, I don't know what's the story with that. In general, it is this is an issue with Lisp languages, because for Lisp you got the same problem, because for the C or CPP or Java people, they can just create a program that can be run on other machines. But for Lisp, usually that you cannot do that. You have to go through something. It's not usually done. So that's the issue. Anyway, let's see if I can, you need to turn on JavaScript in order to copy this. Okay, so I mean, there's so many things. I was gonna trying to show a machine learning stuff. Okay, so it didn't copy. Yeah, there's problems with I think if you have cookies off, the copy doesn't work. So you need to use a browser where you have cookie on. So let's magnify and oh yeah, actually they show the machine learning here. You see, create a plot that looks similar to that. This is a Wolfram language plugin for Chat GPT. So then it generates a code here. I haven't tried it. I don't trust this Chat GPT thing. But anyway, I wanted to show resource function. That's not what we want. What is this? Can we actually do it? Yes, but you need, what is this tool video? New in version 14. Tools 3D geometry. Animation video is based on computing each frame in a video by evaluating an expression. Another class of video generators take an existing visual construct and simply tool it. Oh, okay. So you just pass this function a video. That's another thing no other programming language does. You see, most programming languages, they deal with text. You can't You can't paste in a graphics, but Wolfram language can. You actually paste, visually you are seeing a image as the input to this function, but actually that image is actually a structured, input of a video. But in a Wolfram front end, you see it like that. So anyway, that's not what I want. We want let's copy that. Oh God, we need to turn on JavaScript. Shit. Okay, copy. God, this copy now copied. Okay. Never worked. Let's see if that works here. No. No, it didn't work. I'm not gonna. Actually, we can just type it directly. Okay. Let's just run it. Oh, you need some argument. Random tree code with 0 argument. You need 1 argument or 2. So let's see what is the argument. Okay, you don't want that. You want random tree. Random tree n. Give a pseudo random tree with n nodes. Okay, that's what we want. Let's say 20. Fantastic. Let's get the output. No. But anyway, so that's that. So we were going to try to show a machine learning feature. Okay, so yeah, let me show that, and that's it. Oh, random tree is actually experimental. Okay, it's interesting. So yeah, let's go to random tree is, what version is it? Random tree came from version 12. I don't have it in my Wolfram XR Wolfram mod. Why is it experimental? But anyway, so I want to show so let's go to documentation. Let's go to machine learning. Machine learning overview. Okay, let's go to overview. Predict, classify, find cluster, feature extraction. There's some interesting, let me just quickly show. Okay, feature extraction. In JavaScript, sometimes you see this. You see, this happens on Twitter and other websites. It's stupid JavaScript. Predict. So what is a find cluster? Feature extraction. Is it not feature extraction? Find clusters. Okay, no, not find clusters. Classify. No. Oh yeah, I was trying to do this. Okay, let's try this. So it creates a bunch of images, each one of these. So let me show you what this means, okay? Alphabet is just returns a string, a list of strings, okay? Then rasterize, so this syntax means, it means turns a string into a image, okay? What? Okay, so let's say B. Okay, so this B is a image. Okay, it turns a string into image. Let's say something. Okay, so you can see. So now you map this rasterize into a list of alphabet strings. Okay, that's what that means. So image is a list of images. Okay, so what you do with this machine learning command, feature space plot, is that it automatically arrange the images into categorize the images so that the similar ones are grouped together. Okay, so you have a bunch of alphabet, they automatically group them by their features. So we can see N and H are close, B and P are close, Y is by itself. So Y is kind of unique in English alphabet in terms of shape, lowercase. So that's what's interesting. Okay, so let's try this again. For example, so right now we are trying some of the examples they gave, right? So for these examples, obviously they tried it and it shows it works. So what's interesting is that you want to, we need to do this in another video. You want to use this feature space plot, but you want to give it one bunch of, let's say, your photos and see how they arrange it. In order to do that, I need to get, a bunch of photos. So, for example, you can, you have to get a bunch of photos. But let's try if we can do this quickly, okay? Yeah, let's try Unicode, okay? So let's try some Unicode. Let's see, okay? Letters. So we want mathematics, okay? So let's go to mathematics, or let's get, okay, let's try a bunch of these, okay? Korean characters. Let's get the Korean characters, and let's get a bunch of emoji characters, okay? Copy that. And let's get a bunch of crosses, okay? Interesting crosses. Okay, and let's get a bunch of Latin characters. Okay, let's grab them. This is gonna be interesting. We're gonna turn each of these into a string, then turn each of the string into an image, and then we're gonna use the feature space plot machine learning to see how it groups them. So we also, let's try, okay, let's try some Japanese. Okay, let's grab just this. Okay, then there's a Shavian, Phoenician. Okay, I think that's enough. Okay, let's do this. So I want to turn them all into, what is this? So tab, query replace tab by space. Okay. Tab by space. Okay. And turn them into a line. So now, so we got, now change double empty line by a single empty line. Okay. Okay, then we have, okay, let's magnify. So each character is on a line by itself. You can see, let's remove those. Okay, anyway, so now we do this. So we put a double quote and put a comma, so each one becomes like that. And then we combine them all. So we got this. Okay, then we just add a list. Okay, so we want to remove some of these. Copy that, paste in Wolfram language, see if we got the syntax correct. Correct. Okay, so we got a list here. Yeah, we got syntax copy. Make sure we got it right. Okay. Well, God. Let's try it again. Yeah, okay. So we got a list. Now we want to say map rasterize. Okay. Rasterize function apply to images equals to, yeah, wait, chars. Okay, chars is a bunch of characters, and rasterize chars, so images equals to that. Okay, copy that. Oh, then we just say what is a plot? Feature space plot. Okay, feature space plot images. Copy, or actually copy that. Run it. Oh, we got an extra comma here. Yeah. It worked. Okay, so wait, even extra comma it worked, because yeah, it's null. Okay, so that's special. Okay, so anyway, then let's just plot it. Let's see what it comes. Wow, look. So it puts all the emoji colored ones together. Then it puts, okay, some cross and Japanese together. Then you see all the Latin A variation here. They put them together, so it's pretty good. Then here's a lowercase a grouped together. So machine learning function feature plot in one, here, that's what it is. Fantastic. Okay, bye guys.